Okay, we're going to take a quick break from going through new rules of differentiation and we're going to apply them to weird trig functions. Nothing too crazy like tan 17x or anything involving e's or anything weird like that, but rather the 6 kind of weirder trig functions that we encountered when we did trigonometry. So they are sec, cosec, cot, arcsin, arcos, and arctan. We're going to differentiate all 6 of those one by one. In my previous videos, I've shown the derivatives of sine, cos, and tan. So if you need help with those, go back and have a look at those past videos. But for today, we're going to have a look at sec, cosec, cot, and then arcsin, arcos, and arctan. So let's start off with cosec kx. So I'm going to put a k in there just to cover every possibility of any kind of number associated with that x. So it's important to remember that cosec is the same as 1 divided by sine. If we ever get confused, just remember the third letter law. Our third letter is an S. S stands for sine, so it is 1 over sine kx. Now, here I have got a fraction, I have got a quotient. So I am going to want to use the quotient rule. Even though it's only a 1 on top and it's nothing crazy like we've dealt with before, it's still a fraction, quotient rule still applies. So let's remind ourselves of what the quotient rule is. I'll just stick it over here. If I have a function f of x divided by g of x, then to differentiate that, remember my way of memorizing it, I take the bottom and that stays on the bottom but squared, and then because he's been on the bottom twice, he gets to go first. So we get g of x times by f prime of x minus f of x times g prime of x. That's my quotient rule. So let's map that to this. So my top number, my f of x is 1. So my f prime of x, well, the derivative of a constant, there's no x involved, is just 0. From the bottom, my g of x is sine of kx. And the derivative of sine of kx, hopefully remember, is k cos x. Yeah? Again, if you're not happy with that, go back to my video on differentiating sine and cos, or my video on the chain rule, both of which include this stuff. So now let's map all of this into here and see what we get. So we have g of x first, or g of x is sine kx, times by f prime of x. F prime of x is 0, minus f of x, which is 1, times g prime of x, which is k cos kx. All of that divided by gx squared, which is sine squared kx. Okay, now let's simplify this. Well, sine kx times 0, that's just going to be 0, so that's going to disappear. So on the top, I'm going to have minus 1 times k cos kx. And on the bottom, sine squared kx. Okay, now this is technically my answer, but I can simplify it a little bit more, make it a little bit more manageable. So what I'm going to do is I'm going to separate the bottom. I'm going to keep the top the same for now, and separate the bottom into 2 signs. Sine of kx times sine of kx. And I'm going to divide one of these by cos. Now, if we remember, sine over cos, ignoring the arguments here, is tan. So cos over sine is 1 over tan. And 1 over tan is cot. So we should end up with minus k times cos divided by sine, which is cot. They've got the same argument, so I can divide that. So minus k cot kx. And then I'm left with a 1 over sine kx, and 1 over sine kx is cosec of kx. So my final answer for this first one here, the derivative of cosec k of x, no matter what k is going to be minus k cot kx cosec kx. Okay, next one, let's do sec. Be a bit faster this time because it is the exact same process. Sec, third letter is c, so it is 1 over cos kx. Once again, I've got a fraction. So quotient rule again, I've left it up over there. My f of x is 1 and my f prime of x is 0. Once again, that's going to be the same. And my g of x is cos kx and my g prime of x, well, cos differentiates into negative sign, so it'll be minus k sine kx. Looks awfully similar to the last one because sine and cos transform into each other when we differentiate. So let's pop all of this into my formula again. So I start with g of x is cos kx times f prime of x is 0. So I'll say bye to him in a minute. Minus f prime of x is 1, I won't even bother writing that down, times g prime of x, which is minus k sine kx, all divided by my g of x, which is cos squared. So cos squared kx. Once again, this guy is going to disappear because that's just 0, something times by 0. Then over here, I've got a minus minus, so I just end up with k sine kx. And once again, same as I did with the cosec, I'm going to do a little trick and I'm going to split this cos squared into cos of kx times cos of kx, and I'm going to do the exact same thing. So let's bring this k out so that k can stay there. I then have sine divided by cos. Sine divided by cos is just tan, no weird cot nonsense this time. So I get tan of kx, and then I'm left with, there's a secret 1 there, 1 divided by cos of kx, which is sec of kx. So my derivative of this one, of sec of kx, is simply k tan kx sec kx. Very similar to the cosec one, as would be expected, because realistically, we're just kind of flip-flopping between sine and coses. Now let's do cot. Cot of kx, you know the drill by now. This is 1 divided by tan of kx. Quotient rule, it's a divisor. So let's go. F of x is 1, f prime of x is 0, g of x is tan kx. Now, the derivative of tan g prime of x, I have proven in my quotient rule video. So if you're not happy with the derivative of tan of x, please go and rewatch that video. But for now, I'm just going to state that it is k sec squared kx. Okay? Tan differentiates into sec squared, bring out the k. Right, now let's very quickly throw it all into this formula. So first term, g of x is tan kx times by 0 again. So that's going to disappear. Minus f of x, which is 1, times g prime of x, which is k sec squared kx, all divided by tan squared kx. This guy's going to disappear. As we should be noticing at this point, there's always a 0 in the beginning. That guy's going to disappear. And I'm just left with minus k sec squared kx over tan squared kx. Now, whenever we have a cos, a sine, and or a tan, and they are all, including sec, cosec, and cot, because they also are sine, cos, and tan, and they have the same argument, so the same thing inside the function, so both got kx, and they have the same power, I immediately should be thinking, is there any way I can simplify them? Because we know that sine squared over cos squared, just ignoring the arguments for now, is tan squared. So let's see what I can do with this. Well, sec squared is 1 over cos squared. So this thing here is minus k 1 over cos squared kx divided by tan squared of kx. So I'm dividing by tan, so I can flip it and I can bring my tan down here, and I get minus k over cos squared kx tan squared kx. My handwriting down there is amazing. And looking at this formula here, well, if I bring my cos to this side, cos squared times tan squared is just sine squared. So this is minus k over sine squared kx. And we'll add that in. Ooh, there we go. And 1 over sine squared is simply cosec squared, so my answer is minus k cosec squared kx. Okay, now let's start our inverse. So let's start with y equals arcsin of x. I'll just do x for now and not k, partly because I had to re-record the last bit about 7 times because I kept forgetting k, but also because at this point I'm sure you can just work through with the k and it works out the same. I just want to get the general idea of how to solve this. Now, the general idea is I'm going to start off by rewriting this. I'm going to say, well, if y is equal to the inverse sine of x, then x is equal to sine of y. Okay, this is just by definition. You can think of it as I'm taking the sine of both sides. So sine of y equals sine of the arcsine of x, which will cancel into just x. Or you can think about it the same way that you've been using inverse sine and coses for a number of years. But overall, I end up with x equals sine of y. Now, I'm going to find dx by dy. And we haven't actually done this. I've never done this in a video, which is instead of finding dy by dx, I'm going to find dx by dy. Because if you think about it, my x and my y have kind of switched places. It used to be y equals something, now it's x equals something. So that's the main thing my equation is equal to, so it's going to go on the top. And then the variable I'm concerned with is no longer an x, it's now a y. So sine, we should know, differentiates into cos. So dx by dy is simply cos of y. Okay, but now this doesn't really help me, right? Well, from here I can use another little trick, which is, and if you're a pure mathematician watching, then look away, because this is horrible. But we're going to pretend that dx dy is a fraction. It's not a fraction. It kind of is, but it isn't. Depends on who you ask. But in physics, we do a lot of cancelling with the fractions, and the mathematicians don't like us for it, but here it's fine. So treating it as I would any other fraction, I can say that, well, if I reciprocate this, I'm going to get the other way around. So dy by dx is just 1 divided by dx by dy. Meaning, dy by dx here is equal to 1 divided by this. So 1 divided by cos of y. So I've now got a dy by dx. But this dy by dx contains a y in it. And usually they contain an x, and realistically they should contain an x. So I need to change that. I need to change that and turn this into an x somehow. And I'm going to do that using this fact here. This fact that x is equal to sine of y. Now, x is equaling sine of y, transforming into cos of y is a little bit tricky. The way we're going to have to do that is find the only relation that has just cos and sine in it. Because sine over cos equals tan isn't going to help, because then we're going to have a tan floating about, and we don't want that. So I'm going to have to use sine squared x plus cos squared x equals 1. And I'm going to do some rearrangement here. So I'm going to apply that to this cos here. So in reality, I'm going to replace those with a y, because that's the variable that I'm working with. And I'm going to rewrite this as cos y. So let's do it slowly. So cos y is equal to 1 minus sine squared y. So cos of y is what is the square root of 1 minus sine squared. I can't just square root both. Please don't do that. I've had people before that would just say, well, square root of sine squared is sine and square root of 1 is 1. So it's just 1 minus, no. Has to stay with the square root because we can't simplify like that. Now, I've got my cos y, so I know that dy by dx is 1 divided by this, but it's still got a y in it. But luckily, I know what sine y is, and sine y is x. So if I replace sine of y with x, I get 1 minus x squared is equal to cos, and if I put that into this equation, I get that my final derivative for arcsine is 1 divided by the square root of 1 minus x squared. Okay, now let's do the same thing to y equals arccos of x. If I look annoyed, it's because I recorded this video ages ago, just started editing and realised that this one had an algebra error in the middle of it, and gotta fix it, so let's do it again. Okay, same thing we've just done for arcsine, which is I'm going to write this as x equals cos of y. And then, from here, doing exactly the same method as before, dx by dy is therefore, well, cos differentiates into negative sine, and hence, flipping it over, same as before, to get dy by dx as minus 1 over sine of y. Now, exactly the same method as before, I'm going to want to use the fact that sine x squared plus cos x squared is equal to 1, and I'm going to want to rearrange this for sine, which for some reason I was incapable of doing earlier. Anyway, so let's minus cos squared from both sides and get sine squared x is 1 minus cos squared x. And again, very similar to the last time, I'm going to end up with a square root in there. So sine x is equal to the square root of 1 minus cos of x. If I just flip to the variables I want to use, then sine of y is equal to the square root of 1 minus cos squared of y. Looking very similar to the arcsine one because it is. Now I know what my cos of y is. It is x. So I can replace cos of y with x and I get the square root of 1 minus x squared. So this becomes minus 1 over the square root of 1 minus x squared. Very, very similar to arcsine. And finally, last one, y equals arctan of x. Should know the process by now. Use red, keep it consistent. X is equal to tan of y. Dx by dy. Derivative of tan is sec squared y. Again, for proof of that, check out the quotient rule video. So dy by dx equals 1 over sec squared y. Now, it's a little bit trickier because I know that that needs to turn into an x. So I know that I need to get something here. But how do I write sec squared in terms of tan? Because, you know, sec squared is 1 over cos squared and, you know, it doesn't look immediately obvious. But we have got a trigonometric identity that I have proved in one of my trig videos. So many plugs today. Subscribe as well. There's another plug. I've got a nice identity that is 1 plus tan squared y is equal to sec squared of y. And it's important that if we're ever working with a sec squared and a tan, we remember this. Or we could derive it, but if I just state it, then that works too. So saying this, I don't even need to square root anything because I'm already working with a sec squared. So I can just say that that is equal to 1 divided by 1 plus tan squared of y, and tan of y is x, so it is simply 1 divided by 1 plus x squared. And that is my derivative of arctan.